This is a screencast on topic 2B in Unit 2 for AP Chemistry on bonding. That's the bell, people. Note the difference between intra, which is like an intrastate, for example, highway or freeway within the state, so State Route 20 is within the state of Washington, or inter, which would be like an interstate, for example, I-90 that goes all the way from Washington clear back to the East Coast, goes through all the states. So types of bondings, there's intra, so that is within the compound. Clearly, those are really, really, really strong bonds, and you would have ionic bonds or covalent bonds. And from the covalent bonds, you could have dative or coordinate bonds. On the other side of the type of bonding chart here, we have inter, and that would be bonds, maybe more of the word attractions between the molecules, like maybe one water molecule and another water molecule. So there's hydrogen bonding, which you could think of NO and F. Hydrogen bonding could happen, an extreme attraction, not a true bond, to nitrogen, oxygen, or fluorine. It produces a strong permanent dipole. We haven't talked about that yet. There's dipole-dipole. These are polar molecules. They have permanent dipoles. Or there's LDFs, London dispersion forces. They're nonpolar molecules in which dipoles are induced. So topic 2B, intermolecular forces, people. IMFs is what I like to call them. So the definition of IMFs, forces between different molecules or compounds. There's three types of IMFs. Hydrogen bonding, so NO or F, hydrogen interacting with NO or F. Dipole-dipole, and LDFs, London dispersion forces. Interbonding is based upon the Coulombic attractions between opposite charges, but since the individual charges are usually relatively small, interbonding is a relatively very weak attraction when compared to intrabonding. Electronegativity and dipoles. An electron cloud diagram can be thought of as a probability map of where an electron may be found at any one time. In separate atoms, this is very simple and can be represented as thus. When two atoms join together in a covalent bond, a pair of electrons is shared between the atoms. Each atom within a covalent bond has a property known as electronegativity and is defined as the ability of an atom within a covalent bond to attract electrons to itself. Electronegativity increases from left to right on the periodic table in a particular row and from the bottom of a group to the top. As a result, fluorine is the most electronegative element. If a pair of atoms that are covalently bonded have the same electronegativity, then the electrons in the bond will be completely equally shared, and an electron cloud could be thought of as this. Elements that have electronegativities that are different but very similar, like carbon and hydrogen, are usually considered to be equally shared as well. However, in situations where one atom has a higher electronegativity than the other, then the electrons are attracted toward the more electronegative atom, leading to an electron cloud distortion and a redistribution of electron charge density thus. So this part of the compound is more positive and that part is more negative. The creation of opposite charges at either end of the molecule is called a dipole, and the bond is said to be polar covalent. In the diagram on the previous slide, with no such creation of opposite charges, electrons equally shared, the bond is said to be nonpolar covalent. The presence of dipoles and the intermolecular Coulombic attraction between them determines the type of intermolecular forces present in covalently bonded compounds. In turn, the type of intermolecular forces present can greatly influence the properties. Remember this from first year chem? This chart will not be available on any test for you. Haha. So first year chem, we looked at linear compounds, trigonal, planar, two types of bent, a bent with a 120 and a bent that was a 110. Tetrahedral, remember tetra means four, so it has four parts. Tetrahedral is always at 110 degrees, and then the trigonal pyramidal is 110 degrees. And in this, we had the number of atoms on the center, Na means not applicable, and the number of lone pair electrons on the center, not on the atoms that are attached to the center, but the things on the center. And if you notice, 3 plus 0 adds up to 3. 3 is always tri, as in trigonal. 2 plus 1 is 3. But this particular one is a bent 120. 2 plus 2 is 4. It's a bent 110, because 4 always ends up kind of like a tetrahedral at a 110. And 4 plus 0 is 4. Anytime you have the number 4, it is 110 degrees. And the trigonal pyramidal, 3 atoms on the center, 1 lone pair, it's like ammonia, adds up to 4. 4 things is always at 110. So 4 things is always 110 degrees. 3 things is always 120. And 2, if there is no center, if you just have 2 things, it's linear. More on dipoles. So a molecule with a center of negative charge and a center of positive charge is dipolar. 2 poles, or has a dipole moment. I feel like I have a dipole moment all the time. The center of charge doesn't have to be on an atom. It will line up in the presence of an electric field. Dipoles are drawn with a lowercase delta. See, that isn't pretty? Plus to a negative delta. So you got a delta plus and a delta minus. Which atoms have dipoles? Any 2-atom compound with a polar bond. What compounds with 3 or more atoms have dipoles? There must be a polar bond in the compound. And the geometry, meaning kind of what I referenced on that previous slide, must not cancel it out. So 2 shapes that will not cancel a dipole would be a bent and a trigonal pyramidal. And an example of a bent would be water. That would be a bent 110. And a trigonal pyramidal would be ammonia. So 3 shapes that will cancel the polarity such that there is not a dipole would be something that's linear, like carbon dioxide, but it would have to be linear, and the atoms on either side of the center would have to have probably the same electronegativity. Trigonal planar, again, the atoms around the center thing would all have to be the same electronegativity. Tetrahedral, and note again, all the atoms attached to the center must have the same electronegativity for it to cancel out. So examples of dipoles and dipole canceling. So CO2, carbon dioxide, is linear. It's way over here, and it cancels that pole, so it doesn't have a dipole. But this one, H2COO, has a dipole. It doesn't cancel out the way the electrons are poled. It has a negative part and a positive part. SO3 is trigonal planar, and you get no dipole because it all cancels out. It doesn't look like it would, but it cancels out. Just move on and accept it. Water. This is bent, and there is a dipole. The dipoles are not canceled out. So we have 2 hydrogens, and the oxygens have the electron more than the hydrogen. So the oxygen is electronegative, or it's more negative than the hydrogen, so it has a dipole moment, which is a good thing for us. Ammonia, or NF3, is trigonal pyramidal, and it has a dipole. There's no canceling. And so you have this nitrogen with these 3 hydrogens, or nitrogen with 3 fluorines, and you have these lone pair electrons above the nitrogen. So it has a dipole. It's dipolish. CH3Cl has a dipole. The 3 H's kind of balance each other, but that Cl is negative. If it were, for example, CCl4, where all the parts attached to it were of equal electronegativity, you'd get no dipole, in which there would be canceling out of those. So LDFs. These are small electrostatic forces that are caused by movement of electrons within the covalent bonds of molecules that would otherwise have no permanent dipole. As one molecule approaches another, the electrons of one or both are temporarily displaced owing to their mutual repulsion. This movement causes small temporary dipoles to be set up on the surface of the particles, which then attract one another. These attractions are called London dispersion forces and exist between all atoms and molecules. London dispersion forces increase with surface area and with the polarizability of the atom or molecule. Polarizability, in turn, increases with increased number of electrons. So in short, larger molecules with larger surface areas have more electrons, which have greater polarizability. This leads to more London dispersion forces, greater attractions, and therefore higher boiling points. How LDFs impact boiling points of the noble gases. So on descending group 18, the atoms of the elements get bigger, have more electrons, and have larger surface areas, so they're more polarizable. This increases the London dispersion forces between them, making them more difficult to separate and increasing their boiling points. So if we go, this is like going down even though we're going across here. So helium has a boiling point of -269. If we get all the way to xenon, it's a minus 108. Minus 108 is actually warmer than minus 269. So the xenon molecules are held more tightly together because they have more electrons and they're more polarizable, which increases their London dispersion forces or their attraction for one another. Hence, it's harder to move them apart by boiling. Hydrogen bonding. Hydrogen is an exceptional element in that when it forms a covalent bond, its electron is held to one side of the nucleus, leaving the other side completely exposed. Woo! Any approaching negatively charged group can get very close to the hydrogen nucleus, and this produces an unexpectedly large electrostatic attraction. These electrostatic attractions are exaggerated when hydrogen is bonded to a more electronegative element that is small enough to allow a significant intermolecular attraction. For example, nitrogen, oxygen, fluorine, NOF. Such intermolecular electrostatic attractions are a special type of dipole-dipole force called hydrogen bonds. The occurrence of hydrogen bonds has two important consequences, see below. Both of these occurrences are explained by the increased attraction between molecules caused by hydrogen bonding, making it more difficult to separate them. So one, it gives substances containing them unusually high boiling points, and two, substances containing them tend to be more viscous. Viscous tends to be like more thick, syrup versus water. Example of hydrogen bonding. In water, for example, the red orbs represent the oxygen atoms, and the bluish-gray orbs represent the hydrogen atoms. So the oxygen atoms are partially negative, and they are attracted to the partially positive hydrogen parts. Its attraction's great, isn't it? So boiling points are grouped 14, 15, 16, and 17, and these are hydrides, which means they have hydrogen. So group 14 boiling points. Carbon, Si, and Ge, minus 161, minus 112, minus 90. And then let's just read through this. So for group 14, the boiling point increases due to increased size. So they're bigger, they are more polarizable. It means there's more London dispersion forces. So in a similar pattern of increase in size, dispersion forces, and boiling points is observed amongst group 15 hydrides, except ammonia. Oh, ammonia, because ammonia doesn't cancel out, right? For ammonia in group 15, these molecules are attracted to one another by hydrogen bonds, giving ammonia a much higher boiling point than would normally be predicted if only LDFs were present. I misspoke earlier. So in the NH3, N is one of the NOFs. And so you get more hydrogen bonding, so there's more attraction, and it's more difficult to break them apart. Hence, their boiling point is higher. Groups 16 and 17 over here, these groups resemble that of group 15, with water and HF respectively exhibiting the higher boiling points associated with hydrogen bonding. So here's a graph of boiling points of group 14, 15, 16, 17 hydrides. Vapor pressure. Consider a liquid in a sealed container. Even if the liquid is below its boiling point, a few of the molecules will possess enough energy to overcome the intermolecular forces holding them together and escape into the vapor phase above the liquid. The weaker the intermolecular forces between the molecules, the easier this process will be, and the more molecules will enter the vapor phase. This causes a relatively high vapor pressure. So in summary, weak intermolecular forces cause liquids to have low boiling points. They are said to be volatile and will have higher vapor pressures, and vice versa. Surface tension. If in the body of a liquid, all the particles or molecules experience forces in 3 dimensions around them, this results in no net forces on these particles. However, those particles that are at the surface of the liquid have no particles above them, and as such, they are pulled with a net force into the body of the liquid. This cohesion between particles of liquid causes the liquid to contract to the smallest possible size, a sphere, and creates an internal pressure at the surface that can resist an external pressure. This is why it's possible to float very small objects with higher density than water, type 1 there, on the surface of water, and why water tends to bead into droplets. Oh, I just love a water droplet bead. And look at those paper clips floating on the water. Capillary action. If a liquid is placed into a very thin tube, the combination of cohesive forces within the liquid itself, example like those in the surface tension, and adhesive forces between the liquid and the walls of the tube can add up to overcome the force of gravity, and the liquid can be drawn up the tube without an external force being applied. So both surface tension and capillary action rely upon the strength of the interparticular attraction between the liquid particles. Intermolecular forces in biological molecules. So in order for a substrate to interact with an enzyme, an intermolecular attraction must exist. So in proteins, the primary, secondary, tertiary, quaternary structures will lead to different three-dimensional shapes that, depending on their orientation, may be attracted to polar water molecules, hydrophilic, or repelled, hydrophobic. I think we'll end there, and you can read through those slides on your own, those following ones, because the answers are provided. And until next time, enjoy learning about Unit 2.